Hello, my name is Paul Goodwin, and this is my demonstration project for MAE535, Design of Electromechanical Systems. I'll be doing a demonstration on a brushless DC motor utilizing both a Hall effect sensor and an electromagnet.
There are many benefits to using a brushless DC electric motor over a brush DC motor. There's a reduction in wear because it's a contactless motor, it's high efficiency and low noise. Some of the applications are for segways, electric bicycles, cooling fans, and motion control systems in manufacturing settings. There are two diagrams shown below. The Hall effect sensor generates a voltage potential perpendicular to the flow of current in the presence of a magnetic field. For the electromagnet, when current flows around the coils of the electromagnet, a magnetic field is generated. Here is another view of the Hall effect sensor. You can see that the Lorentz force pushes the electrons to the left side of the sensor, which causes a positive charge to build up on the right side of the sensor. This voltage potential is known as the Hall voltage, and it is what ultimately powers the transistor and the electromagnet for the brushless DC motor. This diagram shows the brushless DC motor with the Hall effect sensor on the right side, the electromagnet on the left side, and the transistor up in the top right corner. When a permanent magnet is not lined up with the Hall effect sensor, there is no Lorentz force to power the transistor and the electromagnet. When the rotor rotates, the Hall effect sensor generates a current that travels to the transistor, which then powers the electromagnet. The electromagnet generates a magnetic field that repels magnet number 4 and causes the rotor to rotate. This rotation then moves magnet number 2 away from the Hall effect sensor, so there's no longer Lorentz force and there's no longer Ampere's law on the electromagnet causing the repelling of the permanent magnet. In this orientation, the rotor is just freely rotating and inertia brings it so another permanent magnet will line up with the electromagnet and Hall effect sensor. There are three main components to the demonstration that you are about to see. The Hall effect sensor operation shows how a Lorentz force causes a voltage potential across the Hall effect sensor which turns on an LED. The electromagnet operation shows the magnetic field generation from the flow of current around the coils because of Ampere's law, and the brushless DC motor will show both the effect of the Hall effect sensor and electromagnet.
As the magnet gets close to the Hall effect sensor, the Lorentz force pushes the electrons to one side of the sensor. This causes a buildup of a negative charge on one side and a positive charge on the other side of the Hall effect sensor. This buildup of electrons on either side of the sensor causes a voltage potential which is perpendicular to the direction of current flow. This voltage potential is known as the Hall effect. I can hold the magnet this way. No matter how close I get, the Hall effect sensor will not trigger the LED to turn on. When I flip it over, the Hall effect sensor causes the LED to turn on.
Here's an electromagnet with an iron core and over 300 turns of magnetic copper wire. When I turn on the electromagnet, it's able to hold on to the drill bit, and when I turn it off, the drill bit falls back down. Here you see the rotor with 4 permanent magnets. Without the Hall effect sensor to turn the electromagnet on and off, the rotor just rotates back and forth and oscillates between 2 of the permanent magnets. Here we see the Hall effect sensor causing the signal to be sent to the transistor and to the electromagnet to generate the repelling force from the electromagnet to cause the rotor to rotate. As it's brought further away, it slows down and rotates because of inertia, and when it's brought close, it speeds back up.